So in this example, let's suppose that f of x is represented by this power series from 0 to infinity, negative 1 to the n times x minus 3 to the n over n plus 1 times 3 to the n. And we want to find f prime of x and the antiderivative of f. Okay, so starting with the derivative. Actually, hold off on that. So first, let me just write this original function. F of x equals that power series there. I guess I'll copy it. But what I want to do is write out the first few terms to give you another way of looking at this. 3 to the n. Okay, so first few terms. Let's see. Let's start with n equals 0. If we plug in n equals 0, you have negative 1 to the 0, which is 1. X minus 3 to the 0, which we're calling that 1. Over, so numerator is just 1. Denominator would be 1 times 3 to the 0, which is 1. Okay, so first term in this sum is just 1. I guess I'll just write it. It's 1 here. Plus, when n equals 1, negative 1 to the first, so I'm going to write a negative in front, x minus 3 to the first over 2 times 3 to the first. So 2 times 3, that's 6. Let me just do one more term. So n equals 2. This will be negative 1 to the second, so that'd be positive 1. X minus 3 squared over, this will be 3 times 3 to the second, right? Which is 9 times 3, so 27. Okay, and it's going to go on from there. What I'm trying to illustrate by plugging in these first few values is that for each value of n, all of this stuff here is generating your coefficient. So we might want to look at this f of x as the sum from 0 to infinity of negative 1 to the n over n plus 1 times 3 to the n. All this stuff that does not involve x, this is a formula that's generating your coefficients in your polynomial. Think of it that way. Times your power of x minus a. So in this case, x minus 3 to the n. So here's your coefficient, here's your power of x. Read it like that. This is f of x. So if we want to take the derivative of a function like that, think about what you do when you take a derivative. With the coefficient, you just leave that alone, right? So this negative 1 to the n over n plus 1, 3 to the n, we would just leave all of that alone. That's just our coefficients. Times you differentiate your expression of x. So when we differentiate this, for some fixed value of n, keep in mind, the n comes down, x minus 3, take 1 away from the exponent there. So here's a power series for f prime. Now one thing, I've skipped finding the starting value. So keep in mind, when n equals 0, in this series, that's just giving me a constant term. And so when I take the derivative, that constant term is going to drop out. And so now this sum should start at 1 to infinity. Another giveaway for that in this problem is the n minus 1 power here. So the derivative, if the function f is essentially this infinite polynomial, then the derivative should also be a polynomial. It shouldn't have negative powers of x. And so the n minus 1 would warn me, oh, hey, I shouldn't be starting with n equals 0 anymore, or I'm going to have a negative exponent. So this sum now starts with n equals 1. But again, the reason for that is because n equals 0 corresponds to a constant term. X minus 3 to the 0, we're just calling that 1, and then everything else here is constant. So the derivative would be 0, would drop out. So that's why that sum starts at 1 there. Okay, let me get this out of the way, and let's talk about the antiderivative, f prime of x. So the antiderivative, we can work that out the same way. So think about how you integrate a polynomial like this. You leave the, let's see, so this is the sum. And again, we can talk about starting values in a minute. But the way you integrate, you leave the coefficient alone. So I could start by just copying down every part of this power series expression that does not involve x. Think of that as, that's part of the formula generating your coefficients. times, and now we take the antiderivative of just the expression of x, so x minus 3 to the n. Antiderivative using power rule for antiderivatives would be x minus 3 to the n plus 1 over n plus 1, right? And this sum would, we're not going to lose terms when you take an antiderivative. In fact, you gain a term. You do that plus c for the constant of integration. So I don't do that thing where I drop from n equals 1 to, or sorry, from n equals 0 to n equals 1 in my sum. It's still going to start at 0 when we take the antiderivative, because you don't lose terms when you integrate. And in fact, you gain that constant of integration. So this could be cleaned up a little bit, but I'm fine accepting this as your final answer for when you're integrating and differentiating a power series. So something like this is fine. Here's your antiderivative, and this down here is your derivative. And again, just keep in mind, it's a matter of separating coefficients times power of x, and then just your regular power rule, either for derivatives, like I did here, or power rule for antiderivatives, like I did here. So it's just coefficient, power rule, coefficient, power rule, when you integrate or differentiate a power series. I can stop the video.